Tonight, in a quiet room somewhere in Maryland, an ordinary Tuesday morning is about to become something else entirely. A single image is loading on a senior astronomer's monitor. The image has traveled across more than 13 billion years of empty space to arrive there. The astronomer leans forward. He stares. He says nothing for a long time. Then, very quietly, almost as if he is speaking to himself, he says 4 words into the empty room. The galaxies are wrong. This is not the kind of sentence astronomers say lightly. They are trained for caution. They are trained to suspect their instruments before they suspect the cosmos. They are trained to reach for the boring explanation first, and the boring explanation is almost always the right one. And yet, in the months that followed that morning, that one quiet sentence began to spread through the field like a low note you can feel before you can hear it. From Baltimore to Tokyo to Cambridge to the high deserts of Chile, scientists kept arriving at the same uneasy conclusion. Something was off, something fundamental, something woven into the very fabric of how the universe was supposed to behave. Tonight, we are going to step gently into that uneasiness. We are going to look at 6 galaxies that, by every law we thought we understood, should not exist. We are going to listen for a strange asymmetry hidden in the way the entire visible universe is rotating. We are going to follow a theory so unsettling that it places our whole cosmos inside the belly of something larger and older than we ever imagined. We are going to meet small, glowing red points that flicker into existence in the infant universe, reign over it for a brief epoch, and then vanish without a clean explanation. And by the end of this journey, we are going to face a possibility that very few cosmologists are willing to say out loud, even though more and more of them are starting to think it. The possibility that the universe we have been carefully measuring for over a century may not be the universe we actually live in. If wandering through these kinds of questions in the dark hours is something that gives you peace, you might consider tapping the like button and subscribing to the channel before we go any further. It helps the next quiet journey find you when you need it most. There is nothing for you to do now. Lower the lights. Let your shoulders drop. We have a long way to walk. We begin. For most of the 20th century, astronomers worked with telescopes that lived on mountaintops. Mountaintops are good places. They sit above part of the atmosphere, away from city lights, and on a clear night, they can show you stars that look almost close enough to touch. But the air still flickers. The wind still moves the trees. And the light from the most distant objects in the universe is so faint, so easily disturbed, that even a perfect mountaintop is not perfect enough. So in the year 2021, on a winter morning in French Guiana, a rocket lifted a different kind of telescope into the sky. It carried a folded mirror, gold-plated, almost 21 feet across. It carried a sun shield the size of a tennis court. It carried instruments tuned to a kind of light most people never think about. Infrared light. The kind of light that carries warmth. The kind of light that travels through dust without flinching. The kind of light that has been wandering across the universe for so long that by the time it reaches us, it is older than our planet, older than our sun, older than almost everything you can imagine. The telescope did not stop at orbit. It kept going. It traveled almost 1 million miles from Earth to a quiet gravitational pocket where it could sit perfectly still and look outward without anything in its way. The Moon, as a comparison, is only about 240,000 miles away. This new telescope was placed 4 times farther out than the Moon. Once it arrived, it slowly unfolded itself, mirror by mirror, like a flower opening in slow motion across the cold dark. Engineers held their breath. They had been working on this machine for almost 25 years. There was no way to send a repair crew. If anything went wrong, there was no fixing it. Nothing went wrong. The telescope, named for a man who once led the American space program, opened its golden eye and began to listen. Almost immediately, in those first early calibration runs, the engineers and scientists noticed something strange. The pictures coming back were sharper than they had hoped for. The faintest objects, the ones they had expected to see only as smudges or hints, were arriving as crisp little galaxies. The instrument was working better than the simulations had promised, and so the team did what every astronomer eventually does when given a powerful new toy. They pointed it at a tiny patch of sky and stared. The patch they chose was small, so small that if you held a single grain of sand at arm's length and pointed it at the sky, the grain would have covered the field of view almost completely. There was nothing in that patch that any older telescope had been able to see clearly. It was a quiet square of darkness, the kind of empty corner of the sky that astronomers like to look into precisely because it is empty. Empty in deep space often means deep. The deeper you look, the older the light is by the time it reaches you. The patch they chose was a kind of cosmic well, and the telescope was about to drop a long, slow rope into it. The first deep field image came back a few days later. Nobody had prepared a press release. What the image showed was not emptiness. It was not even mostly emptiness. The supposedly empty patch was filled with galaxies. Bright ones, sharp ones, galaxies with structure, galaxies with arms, galaxies that looked, at first glance, perfectly familiar. The kind of pinwheels and ellipses and irregular smudges you might expect to see anywhere in the cosmic neighborhood. Except these galaxies were not in our neighborhood. The light from these objects had been traveling for over 13 billion years to reach the new telescope's mirror, which meant we were not looking at galaxies as they are now. We were looking at galaxies as they were when the universe itself was just a few 100 million years old, a toddler, a newborn, in cosmic terms, and the galaxies looked grown up. This is the first crack. This is where the quiet trouble begins. Because in the official story, the story we tell our children, the story written into every textbook, the early universe was supposed to be a slow, dim, fumbling place. The first stars were supposed to be just beginning to light up. Galaxies were supposed to be small, ragged, half-assembled. There should have been a long, slow construction phase, a kind of cosmic scaffolding period, before anything looked truly mature. The image arriving on those Maryland monitors did not show a construction site. It showed a finished neighborhood. Streets, houses, lights on in the windows. A town that had no business existing yet. Within a few weeks, the first papers started landing on preprint servers. Then more papers. Then arguments. Then careful, polite, nervous emails between researchers who had spent decades building the standard model of cosmology and were now staring at images that did not fit it. The arguments are still ongoing. The images keep arriving, and the trouble keeps growing. This is the story of that trouble. Quietly, slowly, told the way a story like this should be told. Not as a scandal, not as a panic, but as a long, careful walk through the implications of what one telescope quietly discovered when it opened its eye and looked back into the deepest part of time. Let us begin with the 6. Soon after the deep field images began arriving, a researcher named Mike Boylan Colchin, an astronomer at the University of Texas at Austin, sat down with a small but unsettling sample. 6 galaxies, all photographed by the new telescope, all sitting at distances so great that the light from them had been traveling for somewhere between 13.1 and 13.3 billion years, which meant we were seeing them as they appeared somewhere between 500 million and 700 million years after the Big Bang. The cosmos, at that age, was supposed to be a hot, restless adolescent, still figuring out how to put itself together. 6 galaxies is not a lot. 6 is a number you can count on one hand and have a finger left over. 6 is a footnote, statistically speaking. But 6 can also be enough. If just one of those 6 galaxies is real, if just one of them really is sitting where it appears to be sitting, then a piece of cosmology cracks. And these were not just any 6 galaxies. Each of them, when the team did the math on their light, appeared to weigh more than 10 billion times the mass of our Sun. Some of them looked even larger than the entire Milky Way. Take a moment with that. Our home galaxy, the Milky Way, has been quietly assembling itself for nearly the entire age of the universe. It needed roughly 13 billion years to grow into the spiral we live inside today. The galaxies the new telescope had found had managed something similar, perhaps even larger, in less than a billion. They were the cosmic equivalent of a child you watched go to bed at the age of 3. And when you came back the next morning, the child was 40, with a job, a house, 2 grown children, and a long and complicated past you knew nothing about. When astronomers looked at the math required to build a galaxy that big in that little time, the numbers refused to cooperate. To produce that much stellar mass that fast, the early gas clouds would have had to convert almost every available atom of hydrogen and helium directly into stars, with virtually nothing wasted. In modern galaxies, this efficiency hovers somewhere around 5%. Most of the available gas just floats. It gets blown around. It heats up. It cools down. It refuses to become a star, ever, no matter how patient the galaxy is. The early galaxies in the new images would have needed an efficiency closer to 100%. Imagine a bakery that turns every grain of flour, every drop of water, and every speck of yeast into perfect bread, with no scraps, no waste, no half-formed loaves. Now imagine that bakery doing it 10 times faster than any other bakery in history. That was the kind of star factory the math demanded. Boylan Colchin, when asked about it, used a phrase that does not sound dramatic until you hear who is saying it. He said that if the masses were right, we were in uncharted territory. From a careful working scientist, the phrase uncharted territory is roughly the equivalent of a flare being fired into a calm night sky. Other researchers immediately tried to find the mistake. Maybe the distances were wrong. Maybe the brightness was being inflated by a few unusually bright stars. Maybe dust was somehow making everything look heavier. Each of these objections was reasonable. Each of them was checked. And one by one, most of them softened, while the central problem refused to go away. Other teams ran their own surveys. A group at the University of Missouri, working through Webb's infrared images, identified roughly 300 candidate objects in the early universe that were brighter than they had any right to be. 300, not 6. Now we were no longer dealing with a handful of strange galaxies that might be flukes. We were dealing with a population, a whole class of objects that did not match the recipe. The recipe, we should pause to remember, is not casual. It is the result of nearly 100 years of careful work. Edwin Hubble's original measurements of expanding space, the discovery of the cosmic microwave background, the slow refinement of cold, dark matter theory, the careful study of how galaxies cluster, how they spin, how they merge. Together, these threads were braided into something called the Standard Model of Cosmology. sometimes shortened to lambda cold dark matter. It is a long, careful, deeply tested story, and most of its predictions have held up beautifully. It says that structure in the universe should grow slowly, building from small to large, like snowballs gathering down a hillside. It says that galaxies in the very early universe should be small, dim, scattered. The new telescope was showing us a sky that did not match. Quietly, scientists began to ask whether the standard model was missing an ingredient. Maybe the very first stars were unusually massive and unusually bright, allowing tiny galaxies to look enormous from a distance. Maybe there was a hidden source of light buried inside these objects that made them seem heavier than they really were. Maybe, and this was the most uncomfortable possibility of all, the recipe itself needed rewriting. Each of these guesses solved part of the puzzle while opening another, and while the field argued over the 6 and the 300, a quieter, deeper, even stranger pattern was beginning to surface in the same data. A pattern that had nothing to do with how heavy the galaxies were, or how bright they were, or how mature they looked. A pattern in the way they were turning. Galaxies spin. That part has been known for almost a century. Spiral galaxies, those great glowing pinwheels that show up on every astronomy poster, have arms that wind out from a bright central bulge. Some of them, when you look at them straight on, appear to spin clockwise. Others appear to spin counterclockwise. The direction is just a matter of which side is tilted toward us and how the arms are coiled. There is no preferred direction in the universe, or so we have always assumed. If you flipped enough cosmic coins, you would expect the count to settle at exactly 50-50. A computer scientist named Lior Shamir, an associate professor at Kansas State University, decided to actually do the count. He pulled images from one of the new telescope's deepest surveys, a project called the Advanced Deep Extragalactic Survey, sometimes shortened to JDES. This survey is a long, patient stare. The telescope returns to the same patch of sky over and over, gathering light from objects so faint that no other instrument has ever resolved them clearly. The result is a kind of cosmic library, page after page of distant galaxies, sharp enough that you can see how their arms wrap and how their disks are tilted. Shamir applied a quantitative method to the spiral galaxies in the survey. He measured the curl of the arms, the orientation of the disks, and the apparent direction of rotation for each spiral that was clear enough to analyze. 263 galaxies passed the cut. 263 little glowing pinwheels from the early universe, each one a question with a definite answer. Clockwise or counterclockwise from where we sit. The result was not 50-50. Roughly 2/3 of the galaxies, around 175 of them, appeared to spin clockwise. Roughly 1/3, around 88 of them, spun the other way. The split was not subtle. It was not borderline. It was not the kind of result you could explain by saying that 1 or 2 galaxies had been miscounted. It was a steady, persistent lean across hundreds of independent objects. It was the cosmic equivalent of flipping a coin 263 times and watching it land on the same face roughly 2 out of every 3 flips. Shamir made a quiet point about how visible this lean is. He said that although the analysis had been done with quantitative tools, the asymmetry in the images is so obvious that anyone scrolling through them, with no specialized training at all, can see it for themselves. You do not need a doctorate. You just need eyes. The pinwheels lean. They lean together. There is a phrase for this in cosmology. It is called a preferred axis. It sounds harmless at first. A preferred direction, a preferred orientation, a preferred axis. Just words. But the meaning is enormous. A preferred axis means that the universe, taken as a whole, has a built-in orientation, a direction, a tilt, something baked in from the earliest moments, surviving through 13 billion years of cosmic evolution, still visible in the way modern galaxies prefer to spin. And this idea cuts directly against one of the deepest assumptions in modern physics. The assumption is called isotropy. It says that the universe should look statistically the same in every direction. No favored angle, no special compass point. No part of the sky more important than any other. Combine isotropy with a sister principle called homogeneity, the idea that the universe is roughly uniform when you zoom out far enough, and you get the foundation of nearly everything else we believe about the cosmos. The Big Bang model rests on this foundation. The math of general relativity rests on this foundation. The shape of the cosmic microwave background rests on this foundation. If you tilt that foundation, even slightly, a long line of dominoes begins to wobble. Some researchers, on hearing about Shamir's result, raised the obvious objection. The new telescope had only looked at one small region of sky. Maybe the asymmetry was a local oddity, restricted to that one window, and the rest of the universe still looked balanced. It was a fair concern, but Shamir pointed out that similar patterns had quietly shown up in older Hubble Space Telescope data as well, in different patches of sky, with smaller samples, but with the same lean. The new telescope had simply confirmed and sharpened an asymmetry that older instruments had only hinted at. There are other strange features of the cosmos that already whisper of preferred directions. The cosmic microwave background, that faint glow left over from the first hundreds of thousands of years after the Big Bang, contains odd alignments of hot and cold spots that some researchers have nicknamed the axis of evil. Large-scale flows of galaxy clusters, sometimes called dark flow, also seem to point in particular directions. Each of these results, taken alone, can be brushed off. Stack them next to the rotating galaxies, and a quieter, older pattern begins to surface. The most boring possible explanation for Shamir's finding is also one of the most consequential. It is a Doppler effect. Our own galaxy, the Milky Way, is moving through space at a few hundred kilometers per second. That motion can subtly brighten the galaxies we are approaching and subtly dim the ones we are leaving behind. If our motion happens to favor one rotational orientation, the count we make of distant galaxies might be biased without us realizing it. If this is the explanation, then the universe is not really lopsided. We just have not been correcting for our own motion carefully enough. But there is a more dangerous explanation, the kind that does not just rewrite a calibration table, the kind that rewrites the universe itself. The universe, if you take Shamir's result at face value, may have been born spinning. The first time you hear it, the idea sounds like a mistake. The universe is supposed to be everything. There is no outside to the universe. There is no before. So how can everything spin? Spin around what? Compared to what? And yet the math allows it. General relativity, the theory Albert Einstein finished a little over a century ago, can describe a rotating universe without contradicting itself. As far back as the 1940s, the mathematician Kurt Gödel, a friend and colleague of Einstein at Princeton, wrote down an exact solution to the equations of general relativity in which the entire cosmos turned slowly around a global axis. Most physicists treated this solution as a curiosity, a toy model, a mathematical possibility, not a physical reality. But the equations themselves do not care about taste. They allow it. They have always allowed it. A truly rotating universe would behave strangely. Light traveling around the rotation axis would bend in unusual ways. In extreme cases, the equations even allow paths that loop back through time itself, returning to their own past. Gödel found this disturbing enough that he used it as evidence that the equations needed something added to them, some extra ingredient that would forbid such loops. Decades passed. Cosmology drifted in other directions. The Big Bang model, with its uniform expansion in every direction, took center stage. Spin became a footnote. Then, more than 70 years after Gödel wrote his quiet solution, the new telescope counted the spirals in the Jades field, found them leaning, and quietly handed an ancient mathematical curiosity, a piece of evidence it had been waiting decades for. If the universe was born spinning, the lean in the galaxies makes sense. The early matter would have inherited the cosmic rotation. Galaxies forming out of that matter would inherit a small bias toward one rotational direction. Not perfectly, because gravity and turbulence and chaos can overwhelm small biases, but as a statistical preference. 2/3 clockwise, 1/3 counterclockwise. Subtle enough to be missed by older surveys. Loud enough, with the new telescope's eye, to finally show up in the count. But here is where the story turns even stranger. A rotating universe needs an external reference, something outside the cosmos for the rotation to be measured against. In ordinary physics, that requirement is hard to meet, because by definition, the universe contains everything. There is no observer floating beyond it with a stopwatch and a compass. Some physicists swat the whole idea away with that single objection. Others see it as a clue, a signpost. They argue that a rotating universe makes sense only if our universe is not the only universe, if something larger contains it. And the most striking version of that argument leads us toward an idea that sounds like science fiction the first time you hear it. It is not. It is a real proposal, with real physicists and real equations behind it. The idea is that our universe was not born from a big bang in the way we usually picture it. It was born from inside something. Specifically, from inside a black hole that exists in some larger, older parent cosmos. If that sentence made you sit up a little, take a slow breath. Lie back. We are about to walk straight into it. The theory has a name. It is called black hole cosmology. Sometimes it is called Schwarzschild cosmology, after the German physicist Karl Schwarzschild, who first solved Einstein's equations for the region around a black hole way back in 1916, in a hospital bed on the Russian front during the First World War. The theory is simple to state and dizzying to absorb. Our entire observable universe, all of its galaxies, all of its dust, all of its time, all of us, sits inside the interior of a black hole that exists in some larger parent universe. To picture this, you have to first picture an ordinary black hole. From the outside, it looks like a sphere of perfect darkness with a sharp edge called the event horizon. Cross the event horizon and you cannot return. From the inside, however, the geometry of space-time stretches and twists in unusual ways. Space and time, which we think of as separate things, swap roles. The center of the black hole is not really a place. It is a future event, unavoidable, like the next moment in your life. In black hole cosmology, the inside of the black hole is not crushed into a singularity. Instead, it expands. Matter falling in does not collapse to a point. It bounces, rebounds, or transitions into a new region of space that begins to grow outward in its own direction of time. From inside that new region, the bounce looks like a beginning. The expansion looks like cosmic inflation. The boundary of the parent black hole, far beyond any telescope's reach, looks like the edge of the observable universe. If our universe was born this way, a number of its strangest features start to make a strange kind of sense. The flatness of cosmic space, which has puzzled cosmologists for decades, fits naturally. Matter falling smoothly into a black hole would arrive smoothly oriented. The expansion that follows would be uniform. The arrow of time, the strange fact that the future feels different from the past, also gets a possible source. Material crossing the event horizon of the parent black hole can only move inward. That one-way motion creates a built-in directional preference. Time inside the new universe inherits it. Yesterday is closer to the boundary. Tomorrow is deeper inside. And the rotation of the parent black hole would imprint a preferred axis on the daughter universe. The very same axis that the telescope's leaning galaxies appear to remember. A theoretical physicist named Nikodem Poplawski, who works at the University of New Haven, has championed this idea for years. When asked about Shamir's rotating galaxies, he did not hold back. He said that the simplest explanation for a rotating universe, in his view, is that it was born inside a rotating black hole. He said he would be extremely excited if the findings hold up. From a working physicist, that quiet admission carries weight. Most cosmologists are not yet convinced. The theory is elegant but light on testable predictions. It is also philosophically uncomfortable. It places our entire universe inside another universe, raising the obvious next question. What is the parent inside of? Some versions of the idea accept an infinite chain. Black holes in our universe spawn new universes. Those new universes spawn more black holes. Each cosmos is a node in an endless tree. Other versions try to close the loop somehow, with the whole structure curving back into itself. The picture is hard to picture. That is a feature, not a bug. The standard Big Bang model is also hard to picture. A point of infinite density expanding into existence is not exactly an everyday image either. We accept it because the math works and the predictions match observation. Black hole cosmology is asking for the same patience. Different math, same demand. Show us the predictions. Match them to data. For decades, no observational test seemed to be within reach. Then the new telescope pointed at a small patch of sky, counted the spirals, found them leaning, and quietly delivered the first piece of evidence that the theory had been waiting for since it was first written down. Poplawski's version of black hole cosmology has a twist that makes the whole picture even stranger. He works with a slightly modified version of general relativity called Einstein-Cartan theory. The change is technical. In standard general relativity, space-time is smooth, and gravity is the curvature of that smooth fabric. Einstein-Cartan adds a property called torsion, a kind of subtle twisting of space-time that appears whenever matter has spin. In ordinary, everyday conditions, torsion is so small that you will never notice it. Atoms have spin, but the gravitational effects of that spin are negligible at human scales. Even the effects on planets and stars are far too small to detect. But inside a black hole, where matter is compressed to almost unimaginable densities, spin becomes powerful. According to Poplawski's calculations, torsion stops the collapse of matter before it reaches a singularity. Instead of a point of infinite density, you get a bounce, a rebound, a new region of space-time that opens up on the other side. That new region, in his framework, is a baby universe. So black holes, in this picture, are not endings. They are doorways. Each one is a passage from a parent universe to a new one. The new universe inherits properties from its parent: mass, rotation, the arrow of time. From inside, observers see a cosmos expanding from a hot beginning. They call it their Big Bang. They build their telescopes. They wonder how it all started. They have no way of knowing, and they live their entire lives inside a structure that, from the outside, is just one more dark sphere in some older sky. Poplawski wrote about this in detail. He pointed out something subtle about the arrow of time. The motion of matter through the event horizon of a black hole can only happen in one direction, inward. That asymmetry, he argued, gets passed to the baby universe through torsion. Time inside the new cosmos has a built-in direction inherited from the parent. We feel that direction every day. Every second is one more step inward, away from a boundary we will never see, toward a future that always lies deeper. Now connect this back to the galaxies. If our universe was born inside a rotating black hole, the rotation axis of that parent gets stamped onto our cosmos. Galaxies forming inside our universe inherit a small bias toward one rotation direction. Not absolute, statistical. About 2/3 clockwise, 1/3 counterclockwise. Exactly the kind of asymmetry Shamir found. When asked about the rotating galaxy result, Poplawski's response was careful but unguarded. He said that a discovery of a preferred axis in the rotation of galaxies would support the theory of black holes creating new universes, and that he would be extremely excited if the findings were confirmed. He did not claim victory. He pointed at the prediction his framework had made and said, "Here is the test, and here is the result." Other physicists are skeptical. Some argue that the apparent asymmetry could come from completely unrelated factors. Selection bias, Doppler effects from our own motion, statistical noise. Each of these alternatives needs to be ruled out before any baby universe theory can be taken seriously. The honest assessment right now is that the evidence is suggestive, not conclusive. One survey. A few hundred galaxies. To prove that the universe was born inside a black hole, we would need many more measurements, in many more fields, with many more telescopes. That work has already begun. Other teams are searching for similar asymmetries in different patches of sky. New surveys are being designed to count rotational directions on samples of millions of galaxies, not just hundreds. The next decade will tell us whether the doorway theory survives. If it does, every black hole you see in a deep field image becomes more than a gravitational monster. It becomes a nursery, a doorway, a quiet portal swinging slowly open into a cosmos that no signal will ever reach back from. And while astronomers debate rotating universes and parent black holes, a quieter, separate crisis has been growing in the same data. A crisis that has nothing to do with spin or with shape. A crisis in something even more fundamental: the speed at which space itself is stretching. Edwin Hubble, working with the Mount Wilson telescope in California in the late 1920s, made one of the most important discoveries in the history of science. He showed that distant galaxies are moving away from us, and that the farther away they are, the faster they recede. The cosmos was not static, it was expanding. The universe had a history, it had a direction, it had a beginning. The rate at which space is stretching got a name. It is called the Hubble constant. It tells you, roughly, how much space is stretching for every unit of distance you measure across. Plug it into the right equations, and you can calculate the age of the universe, the rate at which galaxies separate, and the long-term future of the cosmos itself. For decades, scientists chased that single number. Better telescopes, better methods, more distant galaxies. Each new measurement pushed the precision a little further. By the early 2000s, The value had settled into a comfortable range somewhere around 70 kilometers per second per megaparsec. A megaparsec, in case you are wondering, is roughly 3.26 million light-years. So the number means that for every megaparsec of distance, space stretches by about 70 kilometers per second. Then a problem appeared. Two different methods of measuring the Hubble constant began returning two different numbers. The first method uses the cosmic microwave background, that faint glow of warmth left over from the first few 100,000 years after the Big Bang. Combine those measurements with the standard model of cosmology, run the equations forward through about 13 billion years of cosmic time, and you get a Hubble constant of about 67.4 kilometers per second per megaparsec. The second method uses pulsating stars called Cepheid variables. These are special stars that brighten and dim on a regular cycle. The cycle length tells you the star's true brightness. Compare that to how bright the star appears in our sky, and you get its distance. Use that distance ladder to measure how fast far away galaxies are moving away from us, and you can calculate the Hubble constant directly. This method gives a value of about 73. The two numbers should agree. They do not. The gap is small in everyday terms, less than 10%. In cosmology, it is a chasm. A discrepancy that size means the standard model is missing an ingredient. A force, a particle, a phase of the early universe that the equations have not properly accounted for. The puzzle got a name: the Hubble tension. For more than a decade, astronomers tried to close the gap. Maybe the Cepheid measurements were biased by crowding in distant galaxies. Maybe the cosmic microwave background analysis assumed something wrong about dark matter. Maybe a hidden source of error was inflating one number or shrinking the other. The leading scientist on the local measurement side, a researcher named Adam Rees at Johns Hopkins University, who had already won a Nobel Prize for his role in discovering dark energy, kept refining his Cepheid measurements with the older Hubble Space Telescope. By the year 2019, the precision was tight enough that the disagreement could no longer be explained as random error. The tension was real. The question was just where it was hiding. Then the new telescope came online. It was sharper than Hubble. Its infrared eyes could pierce through the dust and crowded star fields that had haunted the older measurements. If the Cepheid numbers were wrong, the new telescope would expose the error. If they were right, the tension would be confirmed. The team pointed the new telescope at the same galaxies that Hubble had studied. They measured the same stars. They added two new methods, including one that did not use Cepheids at all, but instead used the brightest stars in old galactic populations, called the tip of the red giant branch. 3 independent methods, run on the largest sample of new telescope data collected during the instrument's first 2 years in space. The results arrived in late 2024. The numbers held. The methods agreed. The error was not on the older telescope's side. Rees put it bluntly: the discrepancy between the observed expansion rate of the universe and the predictions of the standard model suggests that our understanding of the universe may be incomplete. The new telescope had ruled out the easy escape. The tension was real. The cosmos was not behaving the way the equations said it should. A puzzle that had simmered for a decade had just become a permanent crack in the foundation. To understand why the Hubble tension matters, picture a recipe. The standard model of cosmology is the cookbook the universe has been following for 13 billion years. Take some hydrogen. Add a generous helping of dark matter. Sprinkle in dark energy. Let it expand. Stir gravity. Bake for 13.8 billion years at extremely low temperature. The cake comes out looking like the cosmos we see today. If the recipe is correct, every measurement of expansion should give the same number, no matter where in cosmic time you look. Measure the early universe through the microwave background. Measure the late universe through nearby supernovae. The two values should match. They do not. The local universe is expanding faster than the early universe predicts. About 9% faster. That is the tension. 9% does not sound like much. Try this comparison. Imagine a clock that loses 1 second every 20 seconds. In a single minute, it slips by 3 seconds. In an hour, by 3 minutes. In a single day, by more than an hour. Apply that kind of mismatch across 13 billion years of cosmic time, and you end up in a different timeline. Galaxies appear in the wrong places. Stars age the wrong way. The cosmic future drifts off the predicted track. So either the early universe measurement is wrong, or the late universe measurement is wrong, or the model connecting them is wrong. The new telescope has now ruled out the first two. That leaves only the third. What could be missing? Some theorists suggest a brief burst of repulsive energy in the very early universe, a pulse of force that puffed the cosmos up faster than standard inflation predicts, then disappeared without leaving a trace. This idea is sometimes called early dark energy. Add this ingredient, and the early universe expansion rate adjusts just enough to bring the two methods into agreement. The trouble is that nobody has ever seen early dark energy. No particle, no field, no clean signal. It is a name attached to a placeholder. The recipe demands an ingredient that has never been weighed. Other theorists go further. They argue that maybe the dark energy we already know about is not constant. Perhaps it changes over time. Recent results from a survey called the Dark Energy Spectroscopic Instrument, which is mapping huge swaths of the sky, hint that dark energy might actually be weakening in our era. If that is true, it would rewrite the long-term future of the universe. The expansion would not accelerate forever. It would slow, stall, perhaps even reverse. The heat death we have been quietly assuming for decades might not be how the story ends after all. Still others propose changes to gravity itself. Maybe Einstein's equations need a modification at very large scales, a correction term that only matters across billions of light years. Modified gravity theories have a long history. Some of them survive for a while. Most of them die. None has yet earned the consensus crown. A few researchers suggest something even stranger. Perhaps the universe simply has different expansion rates in different regions. We might happen to live inside a giant void, a slightly underdense bubble where space stretches a little faster than the cosmic average. Outside our void, the universe could be running a little slower. The Hubble tension, in that case, might be partly a local accident. We just happen to live somewhere where the answer comes out a little high. The new telescope is helping test some of these ideas. Its surveys of distant galaxies are mapping the cosmic web on scales that older telescopes could not reach. Each new measurement either tightens the tension or offers a new hint about what might fix it. So far, nothing has fixed it. The crack is wider, not narrower. Rees and his colleague Mark Kamienkowski, also at Johns Hopkins, have noted that resolving the Hubble tension may also reveal new insights into other discrepancies that have been quietly piling up. The cosmologists are no longer chasing a single mystery. They are watching a small constellation of mysteries reveal themselves all at once, in the same data, at the same time, all connected in ways that nobody fully understands. The early massive galaxies, the rotational asymmetry, the expansion rate. They might be related. They might be telling the same story in different languages. They might require the same hidden ingredient, or they might each require their own. And in the middle of all this, while the field was still arguing about masses and rotations and tensions, the new telescope made another discovery. A discovery so unexpected that it had not even been on the list of things to look for. A new class of object, tiny, red, glowing, and appearing almost everywhere. The first sightings looked like noise. Small, faint, red specks scattered across the new telescope's deep field images. Astronomers initially assumed they were just unusually colored galaxies. Distant. Dust reddened. The kind of background detail you log and move past on your way to something more interesting. Then someone noticed how many there were, and how strange they looked. The objects were nicknamed little red dots. Astronomers, despite their reputation, love simple names. The dots are tiny, a few hundred light-years across at most. Compare that to the Milky Way, which spans roughly 100,000 light-years. A little red dot is to our galaxy what a marble is to a stadium. They glow with a deep red color, suggesting either heavy obscuration by dust or extreme distance, where the expansion of the universe has stretched their light far into the red end of the spectrum. They appear in vast numbers in the new telescope's deep fields. 3 or 4 out of every 100 galaxies in some early universe samples turn out to be one. That is not rare. That is everywhere. They show up around 600 million years after the Big Bang. They peak in number around 800 million years. By 1.5 billion years after the Big Bang, they have largely vanished. Whatever they are, they had a beginning, a reign, and an ending. A short geological era of the cosmos that we never knew existed until the new telescope pulled back the curtain and revealed a whole population of objects hiding in plain sight. The first interpretation was that the dots were active galactic nuclei, tiny galaxies hosting growing supermassive black holes. The black holes pull in gas. The gas heats up. The heat releases enormous radiation. That would explain the brightness despite the small size. But the standard signatures of active galactic nuclei were missing. No clear X-ray emission, no strong variability over time, no flat infrared spectrum. The dots looked like quasars in some ways, and like pure starlight in others. They did not match any single known category. Then a researcher named Dale Kochevsky and his colleagues found high-velocity gas around several of the dots, speeds of 2,000 to 4,000 kilometers per second. That kind of motion is rare for ordinary galaxies. It is common around growing black holes. The gas is being whipped around by the gravitational pull of an enormous central object. The interpretation shifted again. Maybe the dots really are powered by black holes after all. Just a kind of black hole we had not seen before. Compact, hidden, surrounded by enough material to muffle their X-rays and confuse our usual detection methods. The number of dots became the next puzzle. If they all contain supermassive black holes, the early universe must have produced an enormous population of these monsters very, very quickly. Far more than standard models predicted. Some researchers connected the dots, so to speak, with the broader puzzle of impossibly massive early galaxies. Maybe the unexpectedly heavy galaxies and the little red dots are related, both pointing to a population of black holes that grew faster than theory allowed, both suggesting that the recipe for the early universe is missing a critical ingredient. A team led by Fabio Pacucci at Harvard proposed an explanation. The dots could form naturally inside dark matter halos with very low spin. Slowly rotating halos would let gas collapse straight inward, creating dense, compact, luminous red sources. The math fit reasonably well with what the telescope was seeing. Other teams went further. They suggested the dots might be the visible signs of a population of primordial black holes. Black holes formed not from collapsing stars, but directly from the chaos of the very early universe itself. The dots had become a doorway to a much deeper question. Where did the first black holes come from? And the answer kept circling back to a possibility that older cosmology had quietly dismissed for decades. Maybe black holes did not always form from stars. Maybe some of them came first. One of the strangest features of the little red dots is not how they appear. It is how they vanish. Surveys covering the period from 600 million to about 1.5 billion years after the Big Bang find them everywhere. Field after field, image after image. Then, somewhere around the 1.5 billion year mark, the population thins. Within a few hundred million more years, the dots are essentially gone. That is a sharp boundary in cosmic terms. Whatever the dots are, they were a phase, a chapter. Something switched them on. Something switched them off. The simplest explanation is that they evolved into something else. Gas got blown out. Dust cleared. The compact objects grew larger, brighter, and looked like more familiar galaxies. The dots did not vanish in this picture. They graduated. They transformed. They stopped being one kind of thing and became another. That story fits some observations and conflicts with others. Massive, quiescent galaxies, the elderly retirees of the cosmos, sit quietly in the local universe today. If the dots evolved into anything, those retirees are reasonable candidates. Recent results from a new telescope program called RUBIES, led by researchers Anna de Graaf and Gabriel Brammer, suggest that some apparent quiescent galaxies in the early universe may have been undercounted, raising the number of confirmed massive resting galaxies by roughly a factor of 10. The dots, perhaps, are not extinct. They just settled down. Other researchers see something more ominous. They argue the dots could be the remnants of a separate cosmic process entirely, one that does not connect smoothly to later galaxy populations at all. A class of objects with no surviving descendants. A dead branch on the evolutionary tree of cosmic structure. A population that did its work and disappeared, leaving only its echo in the deep fields of the new telescope. The X-ray puzzle deepens the mystery. Active galactic nuclei usually emit huge amounts of X-rays. The dots mostly do not. A few have been detected with weak X-ray signals. One in particular, catalogued by NASA's Chandra Observatory under a long technical name, sits exactly at the location of a little red dot identified by the new telescope. The X-ray energy resembles a quasar. The match was reported in late 2025 and remains one of the strongest links between the dots and supermassive black hole activity. But most dots stay X-ray dark. Their light spectrum looks like a black hole eating gas in some ways, like compact star formation in others, and like something the textbooks have not described in still others. A theory called the black hole star, developed in part by researchers studying the new data, proposes a striking picture. The dots are not galaxies in the usual sense at all. They are enormous, dense clouds of gas with a growing supermassive black hole hidden inside. The gas absorbs the X-rays, which is why we do not see them. The star-like spectrum is the gas itself glowing under the energy released by the black hole within. Imagine a star the size of a small galaxy, with a black hole as its heart. That is the picture. If the black hole star idea is correct, the dots were a cosmic stage. A brief moment when supermassive black holes were forming inside dense clouds, before the clouds dispersed and revealed the monsters within. Once the gas blew off, the structures became normal galaxies with active centers. The dots disappeared because they were a transitional phase, a short window in cosmic time, a glimpse at the moment supermassive black holes were being built. The new telescope caught it, because the new telescope can see in infrared what nothing else can. If this is right, the dots are the closest thing astronomers have to a baby picture of a supermassive black hole. The kind of object that sits at the center of nearly every modern galaxy, including our own. Their formation has puzzled scientists for decades. The new telescope may have just opened the door of the maternity ward. The phrase sounds like a contradiction. A black hole star. Black holes eat light. Stars produce it. How can one be the other? The answer is geometry. A black hole star is not a single object. It is a system. At the center, a growing supermassive black hole. Around it, an enormous cloud of gas. The gas falls inward, releasing gravitational energy as heat and radiation. From far away, the system looks like a glowing ball of gas, like a star. The black hole inside is hidden, wrapped in its own diet. The numbers are extraordinary. Some of the proposed black hole stars stretch a few hundred light-years across. The gas cloud weighs millions of times the mass of our sun. The black hole at the center may already weigh between 100,000 and a few million solar masses. All of this just 600 million years after the Big Bang. For comparison, the supermassive black hole at the center of our own Milky Way, called Sagittarius A star, weighs about 4 million times the mass of our sun. It has been growing for roughly 13 billion years. The black hole stars in the new telescope's images appear to be reaching similar masses in less than 1 billion years. That is not enough time. Not under the rules of normal physics. Black holes grow by pulling in matter, but the radiation given off by the infalling material pushes back. There is a natural speed limit on the growth, called the Eddington limit. At that limit, the radiation pressure balances the gravitational pull, and the black hole simply cannot accrete any faster, no matter how much food is available. To explain the early black holes seen by the new telescope, scientists have had to propose several escapes from this speed limit. Some argue that the early black holes simply broke through, accreting at super Eddington rates for short bursts. Others suggest the early black holes started big. They were not born from collapsing stars at all. They formed directly from the collapse of huge gas clouds, skipping the stellar phase entirely. These would be heavy seeds, perhaps 10,000 to 100,000 solar masses at birth, heavy enough to bypass the slow buildup phase and to grow into supermassive monsters in less than 1 billion years. Then there is the most radical idea. The early black holes were not formed from gas at all. They were formed from the very first moments of the universe itself. These are called primordial black holes. Their existence was first proposed by the Soviet physicist Yakov Zeldovich in 1966, and then developed in detail by Stephen Hawking in the early 1970s. The idea is that in the chaotic conditions of the first second after the Big Bang, dense pockets of energy could have collapsed directly into black holes, without ever needing to become stars first. The masses of primordial black holes could span an enormous range. Tiny ones, weighing as little as 1/1,000,000th of a gram, would have evaporated long ago through the slow leaking process that Hawking himself predicted. Larger ones could persist to the present day, hidden among ordinary matter, invisible except for their gravity. The biggest could weigh thousands or even millions of solar masses, ready to seed the very first galaxies as soon as the universe cooled down enough to let structure form. If primordial black holes exist, They could have served as the seeds for early galaxies. Drop a 1,000 solar mass primordial black hole into a region of dense gas at very high redshift. Surround it with a dark matter halo. Let it grow at extreme rates, and you can build a 100 million solar mass black hole within a few hundred million years. That timeline matches what the new telescope sees. The math has been worked out by multiple teams. A paper by Shiqiang Shen and colleagues at the Hong Kong University of Science and Technology used a Bayesian framework to model how primordial black holes could explain the high redshift telescope galaxies. Their preferred model fit the observations cleanly. Another paper by a researcher named A.D. Dolgov, building on a 30-year-old conjecture he had originally written with Joseph Silk in the 1990s, argued that supermassive primordial black holes could naturally seed both the early galaxies seen by the new telescope and the supermassive black holes seen at the centers of galaxies today. The implication is staggering. If the standard story of black holes is wrong, then nearly every galaxy in the cosmos may be built around a primordial seed, something older than the first star. Something that helped shape the structure of the universe before structure even existed. The black holes did not come last. They came first. In the early 1990s, two physicists, A.D. Dolgov and Joseph Silk, wrote a paper proposing that primordial black holes could form with a particular mass distribution called log normal. The idea was technical. The audience was small. The prediction settled quietly into the literature and waited there for 30 years. Most theoretical predictions in cosmology never get tested in their author's lifetime. The cosmos is large. The relevant times are remote. The technology to make the necessary observations often takes decades, sometimes centuries, to develop. Dolgov and Silk's prediction was different. It got tested by the new telescope. The log normal mass distribution they proposed for primordial black holes turned out to match the masses needed to seed the early supermassive black holes. The prediction, made in the early 1990s by physicists who could not possibly have known what would be found 3 decades later, fit the data the new telescope produced. That kind of match is the gold standard of theoretical cosmology. A specific prediction made before the data exists that turns out to align with what is eventually observed. Dolgov, in his more recent papers, has not been shy about claiming credit for the alignment. He has written that the 30-year-old conjecture not only rescued the standard cosmological model, but in fact predicted the observed rich population of the early universe with developed galaxies and quasars. That phrasing is partly hyperbole and partly genuine pride. The full match between the theoretical prediction and the new telescope's data is not perfect. Adjustments are needed. Other cosmologists dispute aspects of the analysis, but the basic shape of the prediction holds up surprisingly well. The mechanism Dolgov proposes for primordial black hole formation is itself unusual. It does not involve simple density fluctuations collapsing into holes. It involves a complex dance between matter and antimatter in the very early universe, leading to overdense regions that selectively collapse into black holes of specific masses. The details are technical. The result is a population of black holes, formed in the first second after the Big Bang, ready to seed the structure of the cosmos as soon as ordinary matter began to follow them gravitationally. If primordial black holes are eventually confirmed as the seeds of early galaxies, the implications go beyond cosmology. The formation of these objects in the very first moments after the Big Bang would tell us something profound about the conditions of that era. The energies, the fields, the quantum fluctuations that shaped the early universe. Some of the deepest questions about the moment of cosmic birth might find answers in the masses and distributions of primordial black holes. The objects themselves would be fossils, ancient artifacts carrying information about an epoch we cannot otherwise probe. We would, in a sense, be holding the universe's earliest baby teeth in our hands and reading the cosmos's history off the enamel. For now, the case is suggestive but not conclusive. The new telescope's data fits primordial black hole models well. It also fits other models with varying degrees of success. The next generation of telescopes, including the Roman Space Telescope and various ground-based facilities, will help distinguish between explanations. Dolgov, the man who made the original prediction, is in his 80s now. He may live to see his 30-year-old guess confirmed or refuted. Many theorists never get that chance. The new telescope has accelerated the timeline. There is a final wrinkle to the bright early galaxy problem, a wrinkle that reaches deeper than ingredients or seeds or speed limits. Some of the galaxies the new telescope has photographed appear, by certain measurement techniques, to be older than the universe itself. The phrase sounds like a logical impossibility. The universe is roughly 13.8 billion years old. Nothing inside it can be older than that. The math is simple. And yet, several of the new telescope's observations have produced age estimates for individual galaxies that bump uncomfortably against, or even slightly past, the cosmic age limit. The estimates come from analyzing the chemical composition and stellar populations of the galaxies. Old stars produce specific spectral signatures. Heavy elements take time to form, requiring many cycles of star birth, death, and rebirth. By measuring the metal content and stellar ages of a distant galaxy, astronomers can estimate how long it has been forming stars. In some new telescope images, that estimate exceeds the time available since the Big Bang. The conclusion is not that those galaxies are literally older than the universe. That would violate causality. The conclusion is that something in our measurement chain is broken. Either the distance to the galaxy is wrong, or the age estimate is wrong, or the timeline of cosmic expansion is wrong. This is where some researchers have started exploring more radical ideas. One of them is a researcher named Rajendra Gupta, whose work has gained attention by proposing that the universe may be much older than the standard estimate. In a series of papers, Gupta has argued that the cosmos could be roughly 26 to 27 billion years old, nearly twice the standard age. That sounds outrageous. It almost certainly is. But Gupta's reasoning is detailed enough to be worth following at least part way. He combines two ideas. The first is called covariant coupling constants. The constants of nature, like the strength of gravitational interactions and the speed of light, might shift very slightly across cosmic time. If they do, the relationships between observed redshifts and distances would change. The second is an older idea called tired light, which suggests that photons gradually lose energy as they travel through space, shifting toward the red end of the spectrum without requiring expansion. Tired light has mostly been discarded by mainstream cosmology because it fails to match certain other observations. The cosmic microwave background, the patterns of galaxy clustering, the way distant supernovae fade. Each of these behaves like cosmic expansion is real, not like a static universe with photons quietly losing energy. Gupta argues that combining tired light with shifting constants can match all the observations and produce an older universe in which the new telescope's mature early galaxies make sense. They look mature in this picture because they are mature. The universe simply gave them more time. The paper claims that the resulting cosmos does not require dark matter to exist. That is a remarkable claim. Dark matter has been the invisible scaffolding of the Standard Model for decades. Removing it would simplify some puzzles and explode others. Most cosmologists are skeptical. The Standard Model has been carefully tested across an enormous range of observations. Dark matter signatures show up not just in galaxy rotation curves, but in gravitational lensing, in the cosmic microwave background, in the formation of cosmic structure. Removing dark matter requires explaining all of those signatures through other means. Yet the existence of mature galaxies in the early universe creates an opening. If standard physics cannot fit them in, alternative physics gets a hearing it would not otherwise have received. The mainstream response has been to look for ways to rescue the Standard Model. Maybe early stars were brighter than expected. Maybe primordial black holes provided early seeds. Maybe dust patterns made galaxies look older than they really are. Each fix is plausible. None has earned universal agreement. The galaxies older than the universe are a clue. They are also a warning. They sit at the edge of what current cosmology can explain. They push researchers, however reluctantly, toward asking whether the framework, not just the details, might need to change. The idea of tired light is almost 100 years old. In the 1920s, just as Edwin Hubble was building the case for cosmic expansion, the Swiss astronomer Fritz Zwicky proposed an alternative. Maybe distant galaxies were not really moving away. Maybe their light was just getting tired during the long journey across the universe. The proposal had a certain simple logic to it. Photons traveling across vast distances might lose a little energy through some unknown interaction with intervening matter or with space itself. Lost energy means lower frequency. Lower frequency means a shift toward the red end of the spectrum. That redshift could, in principle, be mistaken for cosmic expansion. We would see distant galaxies appearing to recede, when really their light was just running out of breath. Zwicky's idea was tested and largely rejected over the following decades. The cosmic microwave background, the brightness fade of distant supernovae, and the time dilation observed in supernova light curves all behave like real expansion. Tired light has a hard time matching all of them simultaneously. By the 1970s, the mainstream had moved on. The Big Bang and cosmic expansion had won. Tired light became a footnote, mentioned mostly in textbooks as an example of how alternative theories can fail. The new telescope has revived the conversation. Not the original tired light theory exactly, which still struggles with most of the original objections. A modernized version, often combined with other ideas like covarying constants, aiming to address the failures of the simple version while preserving its core insight. Maybe some fraction of the observed redshift in distant galaxies comes from photon energy loss, not just expansion. The motivation is the same as it was a century ago. If standard expansion does not match what we see, alternative explanations get a fresh look. The most common objection to tired light remains the cosmic microwave background. That faint glow, observable in every direction, has a temperature of about 2.7 Kelvin and matches a perfect thermal spectrum to extraordinary precision. Standard cosmology explains this as the cooled remnant of light from the early universe, stretched by expansion. Tired light has a harder time matching it, because photons losing energy through scattering would smear the spectrum. Modernized versions try to handle this by being careful about which interactions cause the tiring. Some only affect certain wavelengths. Others happen only during specific cosmic epochs. Each tweak adds complexity. Each complexity reduces the simplicity that made the original idea attractive. The supernova test is another challenge. Distant supernova fade more slowly than nearby ones. The standard explanation is time dilation. The same effect that Einstein's relativity predicts. As the universe expands, time itself appears stretched for distant events. Light curves stretch with it. Tired light, in its simplest form, predicts no time dilation. The light curves should look identical, just dimmer and redder. Observation shows the dilation. The supernova test was a major reason tired light fell from favor. Yet the early new telescope galaxies have created enough discomfort with the standard model that some researchers are willing to revisit even old, partly discredited ideas. If a hybrid model with a small, tired light contribution can explain mature galaxies in the early universe, it might be worth keeping on the table, even if it has problems elsewhere. The honest assessment is that mainstream cosmology has not embraced tired light. Most papers proposing it remain at the edges of the field, generating attention but not consensus. The new telescope's data is uncomfortable for the standard model, but most cosmologists see the discomfort as a sign that the standard model needs modification, not replacement. Tired light remains a minority view. Its return to the conversation is a symptom of the broader unease in cosmology, not a sign that it is winning. Take Gupta's framework at face value briefly and ask what it would mean if the universe really were 26 or 27 billion years old, roughly twice the standard estimate. The implications are not subtle. The first thing that changes is the timeline of structure formation. Galaxies need time to assemble. They start as dense regions of dark matter, attracting gas, igniting stars, merging with neighbors. The standard model gives them about 13.8 billion years to do this work. The new telescope shows mature galaxies appearing within the first few 100 million years, which strains the standard timeline severely. Double the age, however, and the strain disappears. The mature galaxies become straightforward. They had 13 billion years to grow before the moment we see them. They look mature because they are. The second thing that changes is the role of dark matter. In the standard model, dark matter is the invisible scaffolding that pulls ordinary matter together. Without it, galaxies would not form as fast as they do. The expansion of space would tear gas clouds apart before they could collapse into stars. Dark matter provides the gravitational glue. Gupta's older universe scenario, paired with the covariant constants idea, claims to reproduce galaxy formation without invoking dark matter at all. The slower evolving universe, with subtly different physical constants, accomplishes what dark matter does in the standard picture. Whether the math actually works at every scale is hotly contested. The claim is striking enough to draw attention. If true, dark matter would join the lengthy list of theoretical ingredients that turned out to be artifacts of an incomplete model. Phlogiston, the substance once thought to make things burn, was eliminated when chemistry matured. The luminiferous ether, the medium once thought to carry light through empty space, was eliminated when relativity matured. Dark matter could be next. That is a big if. Most evidence still points to dark matter as a real ingredient. Direct detection experiments, deep underground in old mines and tunnels, have not yet caught one of its particles. But the gravitational signatures are everywhere. Galaxy rotation curves bend in ways that demand more mass than the visible matter provides. Gravitational lensing, where the bending of light by mass reveals the presence of unseen material, shows dark matter's fingerprints in cluster after cluster. The cosmic microwave background carries patterns that fit dark matter cleanly and resist explanation without it. Removing dark matter requires explaining all of those signatures through some other means. Critics argue Gupta's framework cannot. Supporters argue it can. The math is dense, the argument's long, and most working cosmologists are not yet convinced. The third thing that changes is the future. If the universe is much older than thought, then the standard predictions about its long-term evolution may also be off. Heat death, the eventual cooling of all matter and energy into a uniform low-temperature state, might happen on a different timescale. The late acceleration phase of expansion might behave differently. These are speculative consequences. Most of them depend on the details. But even taking Gupta's ideas as a thought experiment is useful. It forces a question that mainstream cosmology has not been forced to ask in a long time. What would it mean if the basic age of the universe is wrong? What would have to change? What would survive? The answer is that almost everything would need to be checked. The age is not a peripheral parameter. It is woven into the calculations behind nearly every cosmic measurement. Change it, and a chain of consequences ripples outward through the entire field. Most cosmologists are not ready to make that change. The standard age of 13.8 billion years has survived an enormous range of tests. The cosmic microwave background, in particular, gives a precise measurement that aligns with that figure when paired with the standard model. But the mature early galaxies whisper a different number. The new telescope has heard the whisper. Whether the whisper grows or fades is the question of the next decade. While astronomers debated rotating universes and parent black holes and tired light and varying constants, another quiet crack widened in the standard model. A crack in the way galaxies look at the very beginning. When the first stars formed in the early universe, they did not form alone. They formed in groups, gathered along the great structures that the standard model describes as a cosmic web. Strands of dark matter, weaving through space, attracting gas. The web shapes everything that follows. Galaxies grow at the intersections. Clusters form where the strands cross. Voids open in the spaces between. In standard cold, dark matter theory, the web is clumpy. Dark matter behaves like a gas of slow-moving particles. They cluster gravitationally into knots and filaments at all scales. Small clumps form first. They merge into larger ones. The hierarchy builds upward. This picture predicts certain shapes for the earliest galaxies. They should be small, roughly spherical, dim. They should grow over time by merging with neighbors, eventually forming the disks and spirals we see today. The new telescope has shown something different. A team led by Alvaro Pozo at the Donostia International Physics Center, with collaborators from Arizona State University, MIT, and Harvard, examined the shapes of young galaxies in the new telescope's images. They found that many of the earliest galaxies appear strikingly elongated, not spherical, not disc-shaped, stretched, prolate, like cigars or footballs rather than balls or pancakes. The team ran simulations to see what kind of dark matter would produce such shapes. 3 models were tested. Cold dark matter, the standard scenario. Warm dark matter, in which the particles move faster and smear out small structures. Wave dark matter, in which dark matter consists of ultralight particles that exhibit quantum behavior on cosmic scales. The cold dark matter simulations failed to produce the elongated galaxies in significant numbers. The warm and wave simulations succeeded. Their cosmic webs were smoother, less clumpy, more like long, gentle filaments. Gas flowing along these filaments naturally formed elongated young galaxies of the kind the new telescope sees. The implication is that dark matter might not be the slow, clumpy particle the standard model assumes. It might be something lighter, wave-like, quantum at large scales. Rogier Windhorst, a Regents professor at Arizona State University, summarized the finding. He noted that in the standard expanding universe, galaxies are supposed to grow over time from small clumps of dark matter that form the first star clusters and assemble into larger galaxies via collective gravity. But the new telescope suggests that the earliest galaxies may be embedded in marked filament structures, more akin to what is expected if dark matter is an ultralight particle that also shows quantum behavior. That is a significant statement. It does not say cold dark matter is wrong. It says the new telescope's observations are more consistent with a different kind of dark matter than with the standard one. Ultralight dark matter has been proposed for years, sometimes called fuzzy dark matter. The particles would be incredibly light, with masses many orders of magnitude smaller than standard candidates. Their wavelengths would be enormous, allowing them to behave like waves on the scales of dwarf galaxies and small structures. Detection has been elusive. Such ultralight particles do not interact strongly with ordinary matter, making them invisible to direct detection experiments. The main evidence has been indirect. Looking at the way galaxies form and evolve, the new telescope has provided new indirect evidence. The shapes of early galaxies do not match the predictions of cold, dark matter. They match the predictions of warmer or wavier alternatives. The cold, dark matter community is not surrendering. There are reasonable rescues. Maybe early galaxy shapes are biased by selection effects. Maybe the simulations need refinement. Maybe small adjustments to the standard picture can reproduce the elongated shapes. But the evidence keeps piling up. Cold dark matter has had a long, successful run. Its first serious challenger in years is wave dark matter, and the new telescope has just handed it a piece of supporting data. Picture what an early galaxy is supposed to look like. The textbooks show small, roughly spherical clouds of gas and stars, gradually accumulating mass through mergers. By a billion years after the Big Bang, you might expect something disk-shaped to begin emerging. By 2 billion years, recognizable spirals. What the new telescope has shown, in many cases, is something else entirely. Cigars, footballs, stretched, elongated objects that look more like compressed lines of light than balls of stars. The shapes are striking. In the Pozo paper and related research, the elongated galaxies appear in significant numbers in the early universe. They are not rare exceptions. They are part of the dominant population at certain cosmic epochs. The standard cold dark matter model has trouble producing these shapes in the right quantities. Cold dark matter forms a clumpy cosmic web. Galaxies forming inside clumps tend toward roundness, not elongation. To stretch a galaxy, you need a smooth flow of gas along a long, narrow channel. Cold dark matter does not provide that channel reliably. Warm dark matter does. So does wave dark matter. Both create smoother filaments in their cosmic webs. Gas falling along these structures gets pulled into elongated shapes as it forms stars. The result is the football-like galaxies that the new telescope sees. The connection between dark matter properties and galaxy shapes is not new in cosmology. Researchers have known for years that different dark matter models predict different patterns of galaxy formation. The challenge was always observing those patterns clearly enough to distinguish between models. Older telescopes could not resolve early galaxy shapes well enough. The data was suggestive but not decisive. The new telescope has changed that. With its sharp infrared eyes, the telescope can resolve the morphology of galaxies as they appeared just a billion years or less after the Big Bang. The shapes are no longer fuzzy blobs. They are detailed objects with measurable axis ratios and orientations. The POSO team examined 6 representative galaxies in their analysis. The top row of their figures showed the new telescope's images of marked filament galaxies. The middle row showed warm, dark matter simulations of galaxies that closely resembled the observations. The bottom row showed cold, dark matter simulations of the same systems. The cold, dark matter simulations did not look like the new telescope's images. The warm, dark matter simulations did. The visual comparison was clear enough to convince several researchers that something needs to change in the standard model. Not necessarily a wholesale replacement of cold, dark matter, but at least a careful reconsideration of which version of dark matter is most consistent with high redshift observations. The implications stretch beyond galaxy shapes. If dark matter is warmer or more wave-like than the standard model assumes, then the small-scale structure of the universe would also be different. There would be fewer tiny dwarf galaxies. The cores of galaxies would be smoother. The rotation curves of small galaxies would behave differently. Some of these predictions can be tested. Surveys of dwarf galaxies in the local universe are looking for the missing satellites that warm or wave dark matter would predict. The matchup is ongoing. Some observations support warmer models. Others support cold, dark matter. The picture is not yet settled, but the new telescope has put a thumb on the warm, dark matter side of the scale. If dark matter turns out to be ultralight, with wave-like quantum behavior on cosmic scales, the consequences ripple through almost every part of physics. The standard candidate for dark matter, the weakly interacting massive particle, would weigh perhaps 100 times the mass of a proton. Ultralight dark matter, by contrast, could weigh 100 trillion times less. The numbers are nearly impossible to picture. Such low-mass particles would have extremely long quantum wavelengths. On the scales of galaxies, the wavelengths could be measured in light-years. The dark matter would not behave like a collection of point particles. It would behave like a continuous wave, oscillating gently across enormous distances. This changes how dark matter clumps. Cold dark matter forms tight, dense halos. Wave dark matter forms looser, fuzzier halos with smooth cores. Galaxies sitting inside wave dark matter halos would look slightly different. The centers would be less concentrated. The outer regions would be smoother. Some observations support this. Dwarf galaxies in the local universe sometimes show flat density profiles in their cores, rather than the steep centers cold dark matter predicts. This is called the core cusp problem. Cold dark matter says cusp. Observation says core. Wave dark matter naturally produces cores. Other observations push back. The cosmic microwave background, the early universe relic radiation, places tight constraints on dark matter properties. Wave dark matter has to be carefully tuned to avoid contradicting microwave background measurements. Some versions survive, others do not. The detection challenge is severe. Ultralight particles do not bounce off atoms. They do not produce visible radiation. They interact almost exclusively through gravity. The main experimental approach has been to look for their wave-like effects on precision instruments. Atomic clocks, for instance, might tick at slightly different rates if surrounded by oscillating dark matter waves. So far, no detection has succeeded. The constraints on wave dark matter come almost entirely from astronomy. Galaxy shapes, galaxy clustering, the cosmic web. The new telescope has added a new line of evidence. The early elongated galaxies and their filamentary surroundings are easier to explain with wave dark matter than with the standard cold version. If wave dark matter wins, physics changes. The weakly interacting massive particle becomes a discarded hypothesis. Direct detection experiments that have been running for decades become historical artifacts. New searches focused on wave-like signatures become the priority. Quantum effects on cosmic scales become a real subject of study, not a theoretical curiosity. The change would not undo Einstein's general relativity. It would not eliminate the Big Bang. It would, however, rewrite a substantial chunk of the picture between those two pillars. The matter content of the universe, the way structure formed, the behavior of galaxy halos. All of it would shift. Most cosmologists are not yet ready for that shift. The case for cold dark matter is built on decades of evidence, much of it consistent with the standard particle picture. Replacing it requires more than one suggestive observation. But the suggestive observations are accumulating. The new telescope has provided several. The elongated early galaxies are one. The hints of unusual galaxy core densities are another. The persistent failure to detect heavy dark matter particles is a third. Add them together, and the case for wave dark matter has grown from speculation to serious hypothesis. When the rotation asymmetry was first reported, an obvious objection appeared. Maybe it is not real. Maybe the apparent excess of clockwise galaxies is an artifact of our own motion through space. The argument goes like this. The Earth orbits the Sun. The Sun orbits the center of the Milky Way. The Milky Way moves through the local group of galaxies. The local group moves through the Virgo supercluster. The supercluster moves through still larger structures. We are not stationary. We are flying through space at hundreds of kilometers per second. This motion has consequences. Light from objects we are moving toward gets blue shifted. Light from objects we are moving away from gets red shifted. The brightness can also change slightly. Objects we are approaching look slightly brighter. Objects we are receding from look slightly dimmer. Apply this to galaxy rotation. A spiral galaxy spinning counterclockwise relative to the Milky Way has parts of its disk approaching us and parts receding from us. The approaching side looks brighter. A galaxy spinning clockwise has the same effect, just with the brighter side reversed. If our motion happens to favor one configuration over the other, we might see more galaxies of one rotational sense, simply because the brighter ones are easier to detect. Shamir himself acknowledged this possibility in his paper. He noted that if the Doppler explanation holds, then we would need to recalibrate distance measurements for the deep universe. The recalibration could explain other unsolved questions in cosmology, such as the differences in the expansion rates of the universe and the large galaxies that, according to existing distance measurements, are expected to be older than the universe itself. That sentence carries a lot. If the rotation asymmetry is a Doppler artifact, it might also explain the Hubble tension. It might also explain the apparent mature galaxies that look too old. A single observational bias, traceable back to the motion of our home galaxy, could be sitting at the root of multiple cosmic puzzles. That would be remarkable. Not a new physics result, a measurement correction. The cosmos would be normal. Our calibration would be off. But the Doppler explanation requires the Milky Way's rotation to have a non-negligible impact on our observations of distant galaxies. Standard estimates of the Milky Way's rotation speed suggest the impact should be small. Too small, in fact, to produce the level of asymmetry Shamir reports. If the asymmetry is real and Doppler-caused, then either the Milky Way is rotating faster than we thought, or our calibrations have systematic errors, or some combination of effects is at play. None of these is a small adjustment. The Doppler defense is the most boring possible explanation for the rotation asymmetry. It is also the explanation that would have the largest practical consequences for everyday cosmology. Rewriting distance measurements would touch every survey, every redshift estimate, every mass calculation that relies on cosmic distance ladders. The alternative, that the universe really has a preferred axis baked in from creation, is more exciting but less well constrained. It would require accepting that the universe was born rotating, possibly inside a parent black hole, and that the rotation imprinted itself on galaxy formation. Shamir does not pretend to know which explanation is correct. He presents both possibilities and lets the data decide. Future observations, with larger samples and more diverse fields, will tell us whether the asymmetry is real or whether it dissolves under closer inspection. For now, the rotation finding remains genuinely uncertain. Both interpretations have implications. Both would change cosmology. If the Doppler explanation for the rotation asymmetry is correct, then the Milky Way's spin is not the small effect that standard estimates suggest. It must be larger, significant enough to bias our view of the entire deep universe. Most astronomers have treated the Milky Way's rotation as a known quantity. The Sun orbits the galactic center at roughly 230 kilometers per second. The orbital period is about 230 million years. We have made one full circuit since the early dinosaurs walked the Earth. These numbers are based on detailed observations of nearby stars and gas. They are not perfect, but they are well constrained by multiple independent methods. Yet Shamir's analysis suggests that the impact of this rotation on our deep space observations might have been underestimated. If the asymmetry he detects is purely Doppler-caused, then the Milky Way's contribution to the apparent brightness of distant galaxies is larger than mainstream estimates allow. This is uncomfortable. It would mean that decades of cosmic distance measurements have a bias none of us noticed. A small but persistent error, traceable to our home galaxy, threading through the published numbers for galaxy distances, masses, and ages. The implications spread quickly. Mass estimates of distant galaxies depend on accurate distances. If those distances are wrong, the masses are wrong. The famously massive early galaxies seen by the new telescope might be less massive than reported. The apparent paradox of mature galaxies in the early universe might soften. The Hubble tension might also be affected. The expansion rate measured locally depends on a chain of distance calibrations. If the chain has a hidden Doppler-related bias, the local rate could be wrong by exactly the percentage needed to bring it into agreement with the early universe rate. That would be an extraordinary outcome. A single hidden bias resolving multiple puzzles simultaneously. No new physics, no exotic dark matter, no primordial black holes required. This scenario has a dramatic appeal, the simplest possible explanation for several cosmic mysteries: our calibration, our blind spot, our error. It also has a difficulty. The bias would need to be quite specific. It would need to affect distance measurements in just the right way to resolve the Hubble tension, while also producing the observed galaxy rotation asymmetry. It would need to leave the cosmic microwave background measurements alone. It would need to fit the supernova data, the galaxy clustering data, and the gravitational lensing data without contradiction. Designing a Doppler correction that does all of this without breaking something else is not easy. Some researchers think it is possible. Others think the Doppler explanation is a red herring, an attempt at simplicity that does not survive detailed analysis. The truth, as usual, will require more data. Larger samples of galaxy rotations, Surveys covering multiple regions of sky, independent tests of the Milky Way's true rotational influence on deep space observations. A study by Shamir himself in 2025, building on earlier work, concluded that astronomers should factor the Milky Way's rotational velocity into observations of deep space galaxies. The recommendation is straightforward. Whatever the correct interpretation, the effect is large enough that it should not be ignored. Whether the rotation asymmetry is a sign of cosmic anomaly or a sign of observational bias, it is teaching us something important. We are not as steady an observation platform as we thought. Our home galaxy moves. That motion matters. Take stock of where modern cosmology now stands. The new telescope's observations have not produced a single contradiction with the standard model. They have produced several. Some of them might be related. Most of them might not be. The mature early galaxies do not fit the standard timeline of structure formation. The supermassive black holes appear too soon for standard seeding mechanisms. The rotation asymmetry hints at a preferred cosmic axis. The Hubble tension persists despite multiple independent confirmations of measurement accuracy. The little red dots represent a population of objects with no clear analog in older theories. The elongated early galaxies suggest dark matter might not behave as the standard model assumes. The galaxies appearing older than the universe itself raise the possibility that the cosmic age is wrong. Each of these is a crack. Each one alone could be patched with careful additions to the existing framework. Together, they suggest that the framework itself might be straining. What might cause all of these cracks at once? Several possibilities exist. None is universally accepted. Each has its supporters and its critics. One possibility is that the standard model is fundamentally correct, but is missing several auxiliary ingredients. Early dark energy, primordial black holes, modifications to dark matter properties. Added together, these might patch the various cracks while leaving the core framework intact. This is the most conservative path forward. It assumes the foundation is solid and only the upper floors need work. Another possibility is that one of the model's foundational assumptions is wrong. Perhaps the cosmological principle, the assumption that the universe is the same in every direction, is mistaken. The rotation asymmetry would naturally fit. The Hubble tension might fit too, if local rates differ from global rates. This is a more dramatic option. It rewrites the foundation while keeping much of the upper structure. A third possibility is that gravity itself behaves differently at large scales than general relativity predicts. Modified gravity theories have a long history. Most have failed. Some persist. The new telescope's data has given new life to several proposals. A fourth possibility, the most dramatic, is that the universe is not what we have been calling it. The black hole cosmology theory, the older universe scenarios, the alternative dark matter models. All of these would represent a substantial rewriting of the cosmic story. Most cosmologists are not yet ready for the dramatic options. The standard model has survived a long stretch of testing. Replacing it requires more than suggestive observations. But the suggestive observations are accumulating fast. Each new image, each new survey, each new analysis adds another data point. The cracks are not closing, they are widening. A senior cosmologist, asked about the state of the field, used a phrase that captures the moment well. He said cosmology is in a renaissance, not a crisis. Exactly. Because crisis implies something is broken beyond repair. Renaissance implies a period of intense rebuilding, where old certainties give way to new ideas, and the boundaries of what is possible expand. The Renaissance has been underway for a few years now. Its driver is the new telescope. The instrument has provided data that no previous tool could match. The data has revealed gaps in our theories. What comes next is the construction of new theories that fill those gaps. Some will succeed. Most will fail. The eventual winner might be a refined version of the standard model with additional ingredients. It might be something far stranger. The galaxies older than the universe, the spinning patterns, the impossible black holes, the disappearing red dots. All of them are clues. The puzzle they assemble has not been solved. The pieces are still being laid out. What can be said is that the universe is more complicated than the standard model predicted. The simplest version of the cosmic story is not quite right. The real story has surprises that nobody anticipated. General relativity is now more than 110 years old. Einstein published the theory in 1915. In the decades since, it has passed every test thrown at it. The bending of starlight by the sun, the orbit of Mercury, the gravitational redshift of light, the slowing of clocks in gravitational fields, gravitational waves from colliding black holes. Each test has confirmed the theory to extraordinary precision. Yet general relativity also predicts its own breakdown. At the centers of black holes, the equations produce singularities, points of infinite density where the math no longer makes sense. At the moment of the Big Bang, the equations again break down. These are not flaws of the theory. They are signposts saying that beyond this point, something deeper must take over. Quantum mechanics, the other great pillar of modern physics, is also more than a century old. Its predictions match experiments with absurd accuracy, yet quantum mechanics and general relativity have never been fully unified. At the smallest scales, where quantum effects should dominate even in gravitational settings, the two theories give incompatible predictions. The search for quantum gravity has consumed generations of theorists. String theory, loop quantum gravity, various other proposals. None has yet produced clear experimental predictions. All of them make claims about the universe at scales far smaller than current instruments can probe. The new telescope does not directly test quantum gravity, but its observations of the early universe, the regime where quantum gravity should matter most, push the boundaries of our framework. The patterns the telescope sees are sensitive to conditions in the very early cosmos. Those conditions, traced back far enough, lead to the quantum gravity regime, the mature early galaxies, the rotation asymmetry, the early supermassive black holes. All of these depend on the conditions of the early universe. Slight modifications to general relativity or to quantum mechanics in those conditions could produce different outcomes. The new telescope's observations might be probing the boundary of where our current frameworks apply. Some theorists are already exploring modified gravity scenarios that affect early universe cosmology. Others are looking at quantum effects on cosmic scales. Each proposal makes specific predictions for what the new telescope should see. The matchup is being checked. So far, no single modified theory has emerged as the winner. The standard combination of general relativity plus the standard model of cosmology continues to provide the best overall fit, though with the various tensions noted in earlier chapters. What the new telescope's data has done is open the door to alternative frameworks. The standard model is not the only game in town. Modified gravity, quantum cosmology, black hole cosmology, ultralight dark matter, primordial black holes. All of these now have a seat at the table. They were always theoretical possibilities. Now they have observations that might support them. Einstein's framework will probably survive. It has too much predictive power to be overthrown lightly. What might change is its application at the largest scales and the earliest times. The framework might need extensions, modifications, additional ingredients. The pattern of how physics evolves is well known. Newton's mechanics worked beautifully for everyday objects. It was extended, not replaced, by Einstein at high speeds and strong gravity. Einstein's gravity might in turn be extended, not replaced, by some future framework that handles the cosmic boundaries better. The new telescope might be helping us identify where those extensions need to go. The view from Earth's perspective is humbling. The framework that has guided physics for over a century is encountering observations that strain its limits. The strain is not yet a break. It is a signal, a request for refinement. Somewhere in the equations or in the cosmos, an answer is waiting. The new telescope has helped us see the question more clearly than we ever could before. Imagine briefly that all the strangest interpretations turn out to be correct. The universe was born inside a rotating black hole in some larger parent cosmos. Its rotation imprinted itself on galaxy formation, producing the observed asymmetry. Primordial black holes formed in the first second after the Big Bang, seeding both dark matter and the first galaxies. Dark matter is ultralight and wave-like, producing smooth filaments rather than clumpy halos. The Hubble tension is real, and it points to new physics in the form of evolving dark energy. If all of this is true, the cosmos is not the universe described in standard textbooks. It is a different place, a place with a parent, a place with a rotation, a place built from primordial seeds rather than stellar collapse, a place where the invisible matter is a quantum wave, not a particle. This is not the cosmos most working scientists believe in today. It is one of several possible cosmoses suggested by current data. Whether it turns out to be correct or not, the fact that it can be seriously entertained is itself a major shift. 20 years ago, almost none of these ideas would have been mainstream. They were on the edges of cosmology, defended by small groups of theorists, dismissed by most others. The new telescope has changed the conversation. The edges have moved closer to the center. The mainstream has expanded to include possibilities it would have ruled out a decade earlier. The implications stretch beyond science. If the universe is one of many, with parent and possibly child universes, the philosophical landscape changes. The question of what is fundamental shifts. Fine-tuning arguments take on new meaning. Anthropic reasoning. The idea that we observe a universe compatible with our existence because no other universe could be observed by us becomes more concrete. If primordial black holes seed structure and constitute dark matter, the bridge between the very early universe and the present cosmos becomes a single object. A black hole formed in the first second, persisting for 14 billion years, anchoring a galaxy, hosting our understanding of the cosmos. That is a different kind of cosmic biography. If dark matter is wave-like, the very small and the very large are connected through quantum behavior. The universe is not a collection of point particles. It is a layered structure of waves, with classical objects emerging from a quantum substrate at certain scales. This is not new in physics. It is new at cosmic scales. If the rotation is real, the universe inherited a memory. The act of cosmic creation was not erasure. Something persisted. The parent cosmos, whatever it was, left a fingerprint that we can still see today, in the way galaxies far from home prefer to spin one way over the other. These possibilities are not certainties. Many of them might fail under closer testing. The next decade of telescopes, including the Roman Space Telescope, the extremely large telescope, and various survey instruments, will sharpen the picture. Some current ideas will be eliminated. Others will be confirmed. New ideas will emerge. What seems clear is that the universe is more complicated, more interconnected, and more strange than standard cosmology suggested. The cosmos does not match a simple recipe. It matches a complex story, with multiple plots, some of them unfinished. The new telescope has been the lens through which the complexity has come into focus. The instrument has served its purpose. It has shown us things we did not expect to see. It has unsettled certainties that needed unsettling. It has prepared the ground for the next generation of discovery. Whatever the eventual answers, the questions are now richer than they were before the telescope launched. Stand for a long moment at the edge of what we now know. The universe is roughly 13.8 billion years old by standard counting. It contains hundreds of billions of galaxies. Each galaxy contains hundreds of billions of stars. Most galaxies host central supermassive black holes. The whole structure is held together by invisible scaffolding called dark matter. The whole expansion is being driven by an even more mysterious force called dark energy. That is the official picture. It has survived a century of testing. It is also showing cracks. The cracks have names now. The Hubble tension, the mature early galaxies, the little red dots, the rotation asymmetry, the elongated young galaxies, the galaxies older than the universe. Each crack has its own literature. Each has its own proposed solutions. What unites them is a shared origin. They were all opened or sharpened by one telescope. The new telescope launched in December of 2021. It parked itself at its observation point 1 million miles from Earth. It began returning images that nobody had quite anticipated. The instrument was designed to study the early universe. It has done that job superbly. It has also done something else. It has shown that the early universe is not what we expected. The differences are not small. They are not within the noise of standard models. They are real, persistent, growing. Whether the standard model will survive the new telescope's data with modifications, or whether it will be replaced by something far more radical, is the central question of contemporary cosmology. The answer will not arrive this year. It probably will not arrive this decade. The data is still flowing in. The theoretical work is still progressing. The arguments are still being made. What can be said is that the next chapter of our cosmic understanding is being written now, in real time. Not in textbooks, in journal papers, conference talks, late-night arguments between cosmologists. The conversation is dense and technical, but it is moving fast. One of the senior cosmologists involved in the discussions described the moment well. He said the new telescope's data is like looking at the universe in high definition for the first time. The signal-to-noise of measurements has improved dramatically. Things that were blurry are now sharp. Things that were ambiguous are now definite. That clarity has come at a cost. The clearer view has revealed inconsistencies that older, blurrier views had hidden. The standard model worked well when the data was less precise. With the new telescope's precision, the seams have started to show. Some of those seams might be sewn back together with careful additions to the theory. Others might require ripping out larger sections and rebuilding. Which seams need which treatment is the question being worked out now. For the rest of us, the takeaway is straightforward. The universe we live in is more interesting than the textbook version. The standard model is not wrong, but it is incomplete. The complete version, when it eventually emerges, will be stranger than what we currently teach. The galaxies are spinning the wrong way. The masses are too large. The expansion rates do not match. The little red dots blink in and out of cosmic time. The dark matter might be a wave. The black holes might be older than the stars. The universe might be sitting inside something larger. Most of these statements would have sounded like science fiction 5 years ago. Today, they are entries in serious cosmological discussions. The new telescope made the transition possible. What comes next depends on the next generation of telescopes, the next decade of observations, the next round of theoretical work. It depends on data that has not yet been collected, ideas that have not yet been formulated, surprises that have not yet been encountered. If the past few years are any guide, the surprises will keep coming. The universe is bigger, weirder, and more honest than we knew. The new telescope has shown us a cosmos that does not fit our maps. The maps are being redrawn. The cosmos is patient. It has held its secrets for billions of years. It is starting, finally, to share them. Let us end where we began. In a quiet room, on an ordinary Tuesday morning, with an image arriving on a senior astronomer's monitor. Light that has traveled across more than 13 billion years to be seen. A small golden eye floating 1 million miles from Earth, looking patiently into the dark. Somewhere in the data it gathers, hidden between pixels, hidden between bright early galaxies and silent red dots and gently leaning spirals, there is an answer. We do not yet know what shape it has. We do not yet know what name it will eventually wear. We do not yet know which of the strange interpretations of our time will turn out to be the right one, and which will turn out to be ghosts. But we do know that we are closer to the question than any generation before us. The universe is teaching us something. It is doing it slowly. It is doing it in its own time. It is doing it the way it always has, through light that takes billions of years to arrive, and patient eyes willing to wait for it. The galaxies are still leaning. The little red dots are still glowing in the deep past. The expansion rates are still refusing to agree. The black holes are still appearing where they shouldn't. The universe is still spinning, somehow, quietly, in a direction that perhaps it inherited from somewhere we will never visit. The new telescope has not solved the cosmos. It has only opened it. For now, that is enough. If this slow walk through impossible galaxies and parent universes and quiet asymmetries kept you company tonight, there is a kind thing you can do for the channel and for whoever might be looking for a journey like this in the future. Tap the like button if it feels right. Subscribe if you would like more of these long, careful explorations of the strangest corners of the universe. And if you know someone who likes to fall asleep to the sound of the cosmos thinking aloud, share this with them. It helps the next quiet journey find the next quiet listener. For now, close your eyes. Let the questions settle. The universe will still be here in the morning, a little stranger than yesterday, a little older, a little more honest, and patient, as always, with the slow species that has only just begun to look back at it carefully. Sleep well. The cosmos is listening too.